Welcome back. In this video, we're going to make some progress on what one of the aims of group theory is. So, an example in our last video that we came across was we were able to say that any group of prime order was cyclic. So that means that if I know that I have a finite group whose order is prime, I automatically know what kind of group it is. It's a cyclic group. So one of the aims of group theory has been to classify the groups of different orders. So if I, for example, if I say, I might want to know what are all the possibilities for a group of order 4 or a group of order 8. And it turns out there are only finitely many different group structures you can have for any given order. And so we're going to make some progress towards this aim in this video by looking at groups of order 2p, where p is prime. So far we know that anything prime is cyclic, so that's cool, we've classified all of those. Now we're going to show that we can figure out what groups of order 2p look like. Okay, so we'll have a preliminary theorem that we'll prove before we actually get into the main one, and then we'll dive into that. Alright, so our first theorem is just one involving a particular set. So I'm going to take two subgroups h and k of a group, and we're going to define the set hk to be the product of all elements, where you take one element h from one group and one element k from the other, multiply them together, collect those all up, and we will have a set. Now I'm not saying it's a subgroup, I'm just saying it's a set, and the order of this set, the theorem is that the order of this set, the number of elements in it, is the order of h times the order of k divided by the order of the intersection of these two sets. Okay, so let's just quickly prove this thing, get it out of the way. So proof. Alright, so let's just take for every t in our intersection. So we're taking a t in the intersection of two subgroups. Then the product hk is also equal to, because t is in both subgroups, I can write that as h times t inverse times k. Now once I've done that, this element here is still in h, this element here is still in k, so I have a number of different choices of writing the same element using different choices of t. Right, so if I take the number of, that means that hk can be written in a number of different ways, at least one for every t in the intersection. So each element in hk is represented by at least that many products in hk. Okay, so our naive estimate for how big this set hk might be would be the number of elements in h times the number of elements of k. But what we've shown here is that actually you get the same element multiple ways by taking different choices of t, and so we have to at least divide that by the intersection of the size of the intersection of h and k. Okay, let's just show that there are no other possibilities here, so that actually it's no longer at least, it has to be exactly. So now suppose that hk is equal to h prime k prime. So now I'm taking two different ways of representing the product hk without making my assumption about this t being an intersection at this point in time. But if this is true, then I can rearrange this to group the elements of h on one side right, and the only way this can be true is if those two things are equal to some element in the intersection, okay? Because here we have a member of h, and here we have a member of k. And so the only way this is true is if they're both equal to some element t in the intersection. So if I have two different ways of writing the same product, they're automatically of the same form as I wrote up here. So actually there are exactly that many. So h is equal to h prime t, and k prime is equal to whatever, no, it's not quite right, sorry. Let's try it again. So H is equal to H prime T and K is equal to, let's just solve that for K, we'll get KT equals K prime, so K is equal to T inverse K prime. K prime T inverse. Goodness me. Alright, thus each element of HK is represented by exactly the order of H intersection K products, and the result follows. Okay, the key thing to note here is, in particular, the intersection divides the product. And that's the fact that we're going to make use of in our next biggish theorem. So that's what we want to keep in the back of our heads. Right, so here is our big theorem for the video, and it is the classification of groups of order 2p. So we have a little bit of information at our disposal now, and it turns out we actually have enough to answer the question of whether or not a group of order 2p, or what possibilities we have for it. So the theorem says that G be a group of order 2p where p is a prime greater than 2. So we're looking at groups of such as 6 or 10, that kind of order. Then there are only two possibilities. Either G is isomorphic to Z2p, it's a cyclic group, or G is isomorphic to the dihedral group of order 2p. And remarkably, that's the only two options that we have available to us. Okay, so this one's going to take a bit of work to prove, so let's get cracking. Okay, so first off, we're going to assume that it does not have an element. Okay, obviously, if it has an element of order 2p, then it's going to be cyclic, right? Because that element will generate the whole group. So if it has an element of order 2p, then it's going to be cyclic. So we'll first assume that it does not have one of these. Okay, once again, if it has an element of order 2p, it's automatically going to be cyclic and isomorphic to Z2p. And we'll show that if this is the case, that it does not have one of these, and it will be the case that G is isomorphic to the dihedral group of order 2p. Okay, so first off, let's just think about what our dihedral group looks like. We expect there'll be an element of order p. So remember D4, that was the dihedral group of order 8. That was the symmetries of a square. There should be an element like R90 that generates the rotations for the group. So we should be able to identify an element of order p inside this group, hopefully. So first we'll show that G must have an element of order p. Okay, otherwise it can't be isomorphic to the dihedral group. All right, so by Lagrange's theorem, which I'll just abbreviate to LT, every non-identity element must have order 2 or p. Okay, because the order of an element must divide the order of the group. The order of the group is 2p. So every non-identity element must have order 2 or p. Okay, and we want to show that there is an element of order P, so we'll assume that there isn't one and find a contradiction. So assume every element has order 2. And now we need to find ourselves a contradiction somewhere. So in this case, a squared will therefore be the identity for each element. Okay, so far so good. In this case, that's got to be true for every element A, and hence, what else can we show with this? AB must be equal to AB inverse. Every element's its own inverse. If every element is order 2, which is equal to B inverse A inverse, which in turn equals BA again, because every element is its own inverse. So G is abelian. So remember, all of this is following from our assumption that every element has order 2. That's given us that every element is its own inverse, and therefore our group has to be abelian, which is a little bit of a surprise. Okay, so let's keep on going and see what we have. What can we do with this? What we're going to do is we're going to build a subgroup of order 4 based on these things. That's going to mess up our assumptions. So now let A and B be distinct elements, non-identity elements. Then, okay, here's the key thing. The set comprised of these 4 elements here, E, A, B, AB, is a subgroup of order 4. Okay, so that's a problem, because remember, every subgroup of our group had to be either of order 2 or of order P or 2P. Remember, the order of a subgroup must divide the order of the group. P is greater than 2, so we cannot have subgroups of order 4. So assuming every element has order 2 leads us to a subgroup of order 4 that we're not allowed to have. So it can't be the case that every element has order 2, and therefore, given that we've assumed we don't have an element of order 2P, there must be at least one element of order P. Okay, so it's a bit of a logical leap. Let's just make a statement. Therefore, this cannot be. So there is an element of order not 2, which must be okay, let's just jump straight to writing P, shall we? Okay, there's an element of order P, because remember, every element has to have order 2P, P or 2 or 1, because those are the only divisors of 2P. Therefore, because we've already ruled out elements of order 2P here, and elements of order 2, they can't all have order 2, so there must be an element of order P. And we'll give this a name, we'll call it A. Alright, so where are we at? We've now assumed that if we don't have an element, we're assuming we don't have an element of order 2P because we already know what happens there. So we now have the key fact that we have an element of order P, and we'll call it A, because this is going to be like the R90. Alright, so what next? So if we think back again to D4, because that's the one we're kind of familiar with, every other element of a dihedral group every element is going to be either a rotation or a reflection. All of the reflections have order 2, and the rotations are rotations. So what we want to do is we want to basically make sure that everything in our group behaves that way. So we're going to choose an element that's not of order P. And not only that, we'll make sure it's not in the cyclic subgroup generated by A. So let B be an element not in the cyclic subgroup generated by A. So basically we're trying to choose a reflection here. Remember, the cyclic subgroup generated by A, that's going to be the subgroup of rotations of our dihedral group eventually. So B, think of B as being a reflection, even though we haven't established that. So by Lagrange's theorem, the order of B equals 2 or P. Remember, it's not 2P because we assumed right at the start we don't have an element of order 2P. Okay, so how do we want to show that the order of B has to be equal to 2. So we know that the cyclic subgroup generated by A is cyclic of order P. Hence, its only subgroups it's got prime order, so its only subgroups are the identity in itself. So far, so good. Because B is not a member of the cyclic subgroup generated by A, the intersection of these two cyclic subgroups must just be the identity, and therefore, now we see why we had that previous theorem, the order of the intersection of these two cyclic subgroups is equal to 1. Now, our theorem that we just proved before, which is 7.2, I think I may have forgotten to label it 7.2, but it is, says that the order of the product set of these two cyclic subgroups is equal to the order of the individual orders divided by the order of the intersection, which we know the denominator is 1, and so this is going to be P, which is the order of the cyclic subgroup generated by A, times the order of the cyclic subgroup generated by B. Okay, so here's where it gets interesting. If the order of B were P, then the order of that product set would have to be P squared. But this is greater than 2P, which is the order of our group. So we can't have our product set having more elements in it than the group itself has, because that's not possible. Which is not possible. So actually we cannot have B being an element of order P, because that leads us to a product set which has order P squared, which is too big, because P squared is bigger than the order of the group itself, and every element in that product set has to be a member of the group, so this is not possible. Hence, the order of B is equal to 2. Right, so it's probably good to take stock at this point in time as to what exactly we've done so far. So we initially assumed that we don't have an element of order 2P, because if we did, we'd be isomorphic to Z2P and we wouldn't have anything left to do. So we showed that that assumption led us to there being at least one element of order P and at least another element, or well, every element in B. Sorry, try that again. There is an element of order P, there must be, we called that A. And then if we generate the cyclic subgroup from A, this one here, then every other element must have order 2. That's what we've shown. So our group consists of an element of order p, which generates a cyclic subgroup. This is like our rotations. And then everything else must have order 2. These are like our reflections. Okay, so at this point in time, we want to actually develop how this group is going to work. So by Lagrange's theorem, we can actually use this cyclic subgroup to partition our group into 2 pieces using cosets. G can be partitioned into, so we're going to take the cosets of the cyclic subgroup generated by A, which is of order 2, which is of order P, so into A and B times the cyclic subgroup generated by A. So every element is of the form A to the K for K between 0 and P, or B A to the K, again for K between 0 and P. Alright, so every element in our group can be written as one of these 2 forms. So what we're going to do is we're going to say, okay, that's great. We've got a way of describing every element of our group of order 2p now. Let's just see if we can figure out the multiplication table of this group, the Cayley table of this group. And if that sort of makes sense, then that will show that if this thing is well defined, given these choices of A and B, that will actually tell us that so long as I can choose those 2 elements, every group is going to behave the same way. So let's see how we can multiply these things out. So first thing we want to note is a little helpful calculation that will be useful for us. So note that B, or A to the IB, is equal to A to the IB inverse, which is equal to B inverse A to the minus I, which is equal to B A to the minus I. Okay, so this is a little construction that we're going to need to make use of from time to time. Basically because we're on the order 2 side of things, this element here is its own inverse, which means if we need to, we can bring B to the other side of an A by using this operation here. Alright, so we've got 3 different cases to consider. First off, we want to see what happens if we multiply together 2 elements of the form A to the K. So A to the K times A to the J is just equal to A to the J plus K mod P, which is well defined. So this is exactly what we'd expect. We expect that when we multiply rotations together, we get kind of cyclic properties, and this is exactly what we see here. What if we take an element of the first form, A to the J, times an element of the second form, B times A to the K? Well, this is where it's helpful to be able to move the B across. Using the construction we just developed, that equals B A to the minus J A to the K equals B A to the K minus J. Again, that is actually mod P. So that gives us an element of the second type, which is, again, no surprise. If I compose together a rotation and a reflection, I get a reflection. Similarly, if I do it the other way around, if I say, maybe I should just group these with parentheses, just so we can see what's happening. If I do it the other way around, B A to the J times one of the form A to the K, I will just get B A to the J plus K mod P. That one's even easier. And last but not least, we need to see what happens if I compose together 2 of these reflection type from the second category. So again, I'm going to shift the B across, so that equals B. So what am I doing there? I'm doing this one here, and I'm going to shift the B across. That's going to equal B times A to the minus J times A to the K equals B squared. That's just the identities. That equals A to the K minus J mod P. Okay, so this is like composing two reflections together. I get a rotation, something in the cyclic subgroup generated by A. Because this multiplication table is well defined, well, it's not really a table, but you could build a table by going through all the possibilities, is well defined, by choosing, and uniquely I should add, by choosing A and B. This says that all non-cyclic groups of order 2p will behave the same way. Two p are isomorphic. And as I've been alluding to, dp is one such group. Yes, remember, all we have to do is choose an element of order p and an element of order 2, and we can build the multiplication table of the entire group just by doing that. Okay, so you might do it as an exercise for D4 and see how that works, but it definitely does. Okay, now if, going right back to the start of our proof, we initially assumed that we did not have an element of order 2, P. If G has one of these, of order 2p, it would be cyclic. And thus isomorphic to Z2p. Okay, so that actually covers all of our cases off. At the very start, we assumed that we did not have an element of order 2p, and that led us eventually to the statement that all of these groups of order 2p are isomorphic, and dp is one of them, therefore all groups of order 2p are isomorphic to the dihedral group of order 2p. If, on the other hand, we had an element of order 2p, much simpler case, our group would be cyclic, and therefore it would be isomorphic to Z2p. Alright, so that's pretty cool. So what we've now shown is that if I have a group of order 2p, there are only two possible structures that it can have. It's either going to be cyclic or it's going to be isomorphic to the dihedral group. So a couple of quick examples. Order of S3 equals 6. We know S3 is not abelian, so it's definitely not isomorphic to Z2p, so therefore it must be isomorphic to D3. Likewise, the general linear group of matrices with entries in Z2 is also of order 6. Remember, there are 8 possible matrices you can make with entries in Z2, but 2 of them are not invertible. And can also show that that is also isomorphic to D3. Okay, so that's just a couple of quick examples, but whenever we have a power, a group of prime times 2, we know automatically that it's going to fit in one of those two categories only. Cool, so that's enough for this video. We will see you in the next one. Okay.